By 2015, the sequence-to-sequence framework had become the dominant paradigm in deep learning. Machine translation, speech recognition, image captioning, all of these tasks were being conquered by encoder-decoder architectures that factorize joint probabilities using the chain rule P of y given x equals the product of P of yt, given all previous outputs and the input x. This formulation is elegant and powerful, but it carries a hidden assumption that both inputs and outputs come in a meaningful sequential order. What happens when your data is fundamentally unordered? Consider a set of numbers, 3, 1, 4, 1, 5. If you want a model to sort them, you have to pick some input ordering. But which one? And when the output itself is a set, say, predicting the ingredients in a photo of a meal, what order should the model generate them in? This paper by Vinyals, Bengio, and Kudlur at Google Brain tackles this question head-on, and the answer is striking: the ordering you choose is not cosmetic. It fundamentally determines how well your model learns. Let's start with the evidence. In English to French machine translation, simply reversing the input sequence, feeding the sentence backwards into the encoder, improves the BLEU score by 5 points. 5 points. Same training data, same model architecture, same number of parameters. The only change is the order of the input tokens. Why does this work? The authors argue it's about distance in the computation graph. When you reverse the input, the first few words of the source sentence are now closest to the decoder, reducing the path length for the most important early predictions. Now consider constituency parsing. You can linearize a parse tree in two natural ways: depth-first traversal, which produces a nested representation like open paren s, open paren np, the cat, close paren, and so on. Or breadth-first traversal, which lists each level of the tree sequentially. Same tree, same information content. But DFT achieves 89.5 F1 on the Penn tree bank, while BFT manages only 81.5. An 8-point gap, purely from how you serialize the same structure. So we've established that ordering matters. Now let's formalize the problem for inputs. A set is fundamentally different from a sequence. The set containing A, B, C is identical to the set containing C, A, B. We need our model to respect this symmetry. It should be permutation invariant. But LSTMs are inherently order dependent. Feed in A then B then C, and you get a different hidden state than if you feed in C then A then B. The representations are different, so the downstream predictions will be different. The naive solution is a bag-of-words approach: embed each element independently and sum or average the embeddings. This is indeed permutation invariant. But it throws away all relational information between elements. The sum of embeddings for quote the cat sat on the mat unquote is identical to quote the mat sat on the cat unquote. We need something more expressive, a model that is invariant to input ordering but still captures complex interactions between set elements. This is exactly what the read-process-write architecture provides. The read-process-write architecture has three components. First, the read step: embed each element of the input set independently. For element xi, compute mi equals f of xi. This is just a learned embedding, nothing order dependent yet. Second, the process step, and this is the key innovation. An LSTM runs for capital T processing steps, but instead of reading input elements sequentially, it attends to all of them at every step. At step T, the LSTM updates its hidden state Qt star. Then it computes attention score ZIT over all memory slots MI, using the current hidden state as a query. These scores are softmax normalized to get attention weights AIT, and used to compute a weighted sum RT over the memory. The final state Qt concatenates the LSTM output with this attention readout. After T processing steps, the model has iteratively refined its understanding of the set, attending to different elements in different combinations. Crucially, the final representation is invariant to the order of the input set, because attention treats all elements symmetrically. Third, the write step uses a pointer network or standard decoder to generate the output, conditioned on this processed representation. To validate this architecture, the authors choose an elegant benchmark: sorting. Given a set of n random floating point numbers, output them in ascending order. This is a pure set-to-sequence task. The input is inherently unordered, and the output has a single correct ordering. The results are revealing. With just one processing step, t equals 1, the model achieves 72% accuracy on sets of 5 numbers. It's learning something, but one pass of attention isn't enough. Increase to t equals 5 processing steps, and accuracy jumps to 94%. The model needs multiple rounds of attention to compare elements and figure out the ordering. Adding glimpses, extra attention operations at decode time, provides further improvement. Perhaps most impressively, the architecture scales. Even for sets of 15 numbers, where there are over 1 trillion possible orderings, the model achieves reasonable accuracy. The processing steps act like internal computation time, letting the model perform the comparisons necessary for sorting through iterative attention rather than through sequential processing. Now let's flip the problem. What about output sets, cases where we need to generate an unordered collection? The chain rule forces us to pick an output ordering, and that choice matters enormously. In language modeling experiments, the authors train models to predict sets of n words. Using the natural left-to-right ordering achieves the best perplexity. Reversing the order makes it slightly worse. But using a random fixed permutation degrades performance significantly. The chain rule decomposition is emphatically not invariant to ordering, even though the underlying set is the same. We saw this with constituency parsing too. DFT at 89.5 F1 versus BFT at 81.5 is a massive gap. And for combinatorial optimization problems like the traveling salesman problem, the output is a set of edges forming a tour. There's genuinely no natural order. Whatever serialization you choose for training will bias the model. These examples converge on a single conclusion: when the output is naturally a set, we need a principled way to handle the ordering problem rather than making an arbitrary choice. To understand why ordering matters theoretically, the authors connect to graphical models. The chain rule factorization P of y1 through yn equals P of y1 times P of y2 given y1 times P of y3 given y1 and y2, and so on, and this corresponds to a specific directed graphical model. It's a fully connected graph where each variable depends on all previous ones. Different orderings of the variables produce different graphical models with different conditional independence structures. A head-first ordering, where the first element conditions everything else, concentrates information in one variable, like a tree with a single root. A random ordering creates an arbitrary dependency structure. Now here's the subtle point: with infinite data, all orderings yield the same marginal likelihood. The chain rule is mathematically exact regardless of ordering. But we never have infinite data. With finite samples, some decompositions are much easier to learn than others. The sample efficiency, how quickly the model converges, depends strongly on the ordering. When the true distribution is peaked and concentrated, ordering matters less. When it's broad and complex, ordering matters enormously. This brings us to the paper's key algorithmic contribution: instead of committing to a fixed output ordering, search for the best one. Equation 9 formalizes this. We want to find parameters theta that maximize the sum over training examples of log p of y under the best permutation pi star, where pi star is the permutation that maximizes the likelihood for each individual example. This is a beautiful formulation, but there's an obvious computational challenge. For a set of n elements, there are n factorial possible orderings. For n equals 10, that's over 3 million. For n equals 20, it's astronomical. Exhaustive search is impossible. The authors propose a practical training strategy. First, pre-train the model using a simple fixed ordering, say, sorted or left to right. This gives the model a reasonable starting point. Then, use ancestral sampling from the current model to generate candidate orderings. Evaluate each sampled ordering's likelihood, and update the model parameters toward the best ones found. This iterative procedure gradually discovers better orderings, guided by the model's own evolving preferences. It's a form of self-improving search. The most elegant experiment in the paper tests whether this search procedure can rediscover a known good ordering. Take 5-word sequences from natural text, 5 grams. Strip the ordering to create sets. Now train a model to reconstruct sequences from these sets using different strategies. Sorting the words alphabetically gives a high perplexity. It's an unnatural decomposition that the model struggles with. A random but fixed permutation does better, but it's still suboptimal because the decomposition doesn't match the true data generating process. Using the ordering discovered by equation 9, the search procedure, the model achieves perplexity very close to the natural left-to-right ordering. The model essentially recovers the natural order of English text, without any supervision about what that order should be. Think about what this means. The search over orderings, driven purely by likelihood maximization, converges to the linguistically natural order. The ordering that humans use to write sentences turns out to be close to the ordering that makes sequences easiest for neural networks to model. Nature's ordering is approximately optimal. Let's step back and see the full picture. This paper makes 3 clean contributions. First, compelling empirical evidence that ordering profoundly affects seek-to-seek performance, both on the input side and the output side. Second, the read-process-write architecture for encoding input sets using iterative attention, permutation invariant by construction. Third, a practical algorithm for searching over output orderings during training, avoiding the need to commit to an arbitrary serialization. The legacy of this work extends far beyond the specific experiments. The read-process-write mechanism directly influenced deep sets, set transformer, and the set-to-set architecture used in molecular property prediction. The idea of attention over unordered elements is a core component of the transformer itself. And the insight that ordering assumptions deserve careful scrutiny has become a guiding principle in modern architecture design. Whenever you use a seek-to-seek model on data without natural order, remember, order matters.